My invisible friends, hello and welcome back to our series on electrical engineering. This is the second video of a sub-series dedicated to electric filters. Previously, we've learned how to classify a filter into low pass, high pass, band pass or band reject, and also into first order, second order filters and such. Today we learned a new classification depending on what we use to build the filter. If we use only passive elements and reactive elements, resistors, inductors, capacitors, we will name that filter a passive filter. It doesn't need any power supply to make it run. If on the other hand, apart from resistors, inductors, and capacitors, it also uses op-amps, then we call that an active filter. Active filters and passive filters, they don't replace one another, they complement each other. According to the textbook by Professors Alexandria and Saidiku, an excellent textbook, the pros and cons of those passive and active filters can be summarized as follows. I have highlighted in green the good comments and in red the bad comments, the bad properties of each one of them. Passive filters are very stable, says Professor Alexandria and Saidiku too. But they may have coils in them, and that is a bad thing, because coils are expensive, they are lossy, they are heavy. For a given characteristic, that means for a given transfer function, we may need to have huge values of capacitors or huge values of inductors. That is a bad thing too. A good thing is that they can operate at frequencies much higher than active filters can. A bad thing, when we load a passive filter, that is when we connect a circuit that drains current out of the filter, the frequency response of that filter changes. We know that from our solution of Bode plots and transfer functions. And finally, at low frequencies, their behavior cannot be that good. For active filters, the main characteristic, positive one, is that they can amplify the signals in the pass band. They can do that, passive filters cannot. They are not affected by loading them. We learned that when we studied op-amp circuits in our previous course. And also, we can design all types of filters, never using a coil, and that is a good thing. On the downside, active filters can be less stable than passive filters, and active filters don't work at very, very high frequencies the way passive filters do. So you see they complement one another. I have a few questions for you on top hat. These are multiple choice. I invite you to work through them before you listen to the answer. What type of a filter is this one on the right? We have seen that filter, one RC filter. That is a what? That is a low pass filter. We have seen that before. But that is more. That is a first order low pass filter. More, that is a passive first order low pass filter. What about this one? Same thing, we've also seen that one. That is a high pass filter. And that is a passive high pass filter. And that is a first order passive high pass filter. What about this one? For this one, I invite you to find the transfer function and draw the Bode plot, and the Bode plot will tell you the type of filter you have. I've done that. Look at the top of the figure. The amplitude plot tells us that this circuit is a low-pass filter. But there is more. Look at that. In 1 decade, the decibels drop 40 decibels. In 1 decade, the drop is 40 decibels, so the slope in the transient zone is negative 40 decibels per decade. This is an order 2 passive low-pass filter. What about this other one? This one. You do the same and you will find that this is a second order high pass passive filter. And more. This one. Well, that one, you do the same. You find the transfer function, you find the Bode plot, and look at the characteristic, and that is a band pass filter. The last one is this one. In this one, when we do the transfer function and the Bode plot thing, what we get is that in our hands we have a band reject filter with a very high quality factor. Why so high quality factor? Because I'm using an ideal inductor in the shunt branch That is impossible. You know that an inductor is implemented with a coil, and coils, apart from inductance, they also have a resistance. So I have to include the resistance in my analysis, and when I do that, then that curve becomes this one, still a band reject filter. Let's connect two filters to see what happens, what kind of a filter we obtain. When we connect the output of one filter to the input of the next filter, we say we have connected them in cascade. We are cascading those filters. The combined effect of those two filters cascaded like that is a new filter. What type of filter? Let's see. Let's explore that. What kind of a filter do we get when we cascade two filters, let's say a low-pass filter and a high-pass filter? Let's look at the amplitude body plot. The filters are characterized by their transfer functions h1 and h2. For h1, the input is x1, the output is y1. For the second one, the input is x2 and the output is y2. In the circuit, we see that y1 is x2, the way it's connected. The behavior of the first filter is given by this equation. For the second filter, by this other equation. But we know that y1 is x2, so we can substitute from the first equation into the second one and say that y2 is h2, h1, h1. So the whole combination behaves as a filter that has the input x1 and the output y2. And the transfer function of the combination is h2 multiplied by h1. When we cascade two filters, we multiply their transfer functions. The implication is that if the first filter has poles A, B, and C, and the second filter has poles at E and F, when we cascade them, and in certain conditions where the load of the second one does not affect the first one, then the whole combination has the 5 poles A, B, C, D, E. In decibels, that equation becomes like this one. So the decibels of the output are the decibels of the input plus that sum. That sum is the body plot characteristic of the sum of the combination, of the cascading of those two filters. That's how we find the type of filter that we have. We draw the decibels plot for each one of the filters and we add them. Let's see how that works for two filters in this slide. A low-pass filter on the top and a high-pass filter at the bottom. At this part of the class, normally I ask for two volunteers. Let's say that the two volunteers are Joe and Mary. And I ask Joe, you will be the low-pass filter. You will be a bouncer to a party, but you will also be a low-pass filter. At that party, you will be the low-pass filter bouncer. You will check that anybody taller than 6 foot, you will send them home. No party for you. And I turn to Mary and I say, Mary, you will be a high-pass filter. You will be a bouncer in Cascade with Joe. Your job is you will send home anybody shorter than 5 foot. You're a high-pass filter. When you're in Cascade, anybody to get in the party has to get the approval of both of you, not only one of you. Do you agree that the people at the party is people that are taller than 5 and shorter than 6 foot? Everybody in the class agrees on that. So when we cascade a low-pass filter and a high-pass filter, we may get a band-pass filter if the corner frequency of the low-pass is higher than the corner frequency of the high-pass. If that is not true, then what we have here, if we cascade them like that, if you think that you're going to get a band stop like that, you are wrong. No, that's not going to happen. The truth is that if you cascade these two bouncers to a party, nobody gets in the party. Everybody is either too tall or too short. Nobody gets in. One way of creating a band reject filter is we send each one of the bouncers to a different door. Yes, the party has 2 doors. The high-pass filter and the low-pass filter. The bouncer that is a high-pass filter is at one door and lets people in only if they're taller than 6 foot. The other bouncer is at the other door and is letting people in only if they are shorter than 5 foot. Anybody who is rejected at one door can go to the other door to see if the other bouncer will let him or her in the party. You agree with me that at the party you have either too short people or very tall people. That's how you implement a band stop a band reject filter. One low pass, one high pass at separate doors. And you must be thinking, yeah, that works with bouncers and 2 doors. How do I create 2 doors in an electric circuit? We use something we learned in our previous courses, summing amplifier. Look, let's say we have those 3 resistors. We have the 2 input resistors, V1 and V2, and the output is V0 on the other end. One more thing is I will make sure that the voltage here is 0 volts, no matter what. How are you going to do that? With an op-amp here. The op-amp will guarantee that Vn is equal to Vp. I ground Vp, so the voltage of Vn is 0. More, the input current to the op-amp is pretty much 0 amps. Good. Do you agree with me that the current on the top left resistor 1 ohm is V1 minus 0 divided by 1? That current is just V1. And the current in the other resistor is V2 minus 0 divided by 1. That is just V2 amperes. So, because the current into the op-amp is 0, then the current on the right 1 ohm resistor has to be the sum of V1 and V2. That is the current there. And that current, according to Ohm's law, will produce a voltage drop in that resistor with this polarity, and the voltage will be V1 plus V2. The voltage on the left is 0. The voltage of V0 is the negative of V1 and V2. So this circuit is adding V1 and V2. And you're saying, hey, it's adding them, but it's also increasing the phase by 180 degrees. Yeah, we can live with that. And if not, we will put an inverting amplifier and rid of ourselves of the negative sign. Those are the 2 doors that we need to connect the 2 electronic bouncers like this. Low pass filter, high pass filter. A signal goes through either through the low pass filter door or through the high pass filter door. The output contains either very low frequencies or very high frequencies. Now you get it, right? Let's see if you know Kung Fu. I have a question for you now. If we connect a simple RC low pass filter, we have seen them, and a simple RC high pass filter through a summing amplifier to reject the band between 500 rads per second and 1000 rads per second. And the resistors in both filters are 10 kilo ohm resistors, not in the summing amplifier. In the summing amplifier, the resistors are 1, 1, and 1. What should be the values of the capacitors if the minimum acceptable rejection attenuation, Amin, in the stop band is 20 decibels? I invite you to solve that. And then, okay, pause, solve it, and now you're ready. Here's the answer. Spoiler alert. Those are the answers. The capacitor in the low-pass filter should be a 2 microfarad capacitor, and the capacitor in the high-pass filter should be a 1.25 nanofarads. Once again, let's review one circuit, RLC, that can be either of the 4 filters. Either connected this way, that way, this way, or this other way. It can be a low-pass filter, a high-pass filter, a band-pass filter, or a band reject filter. Tutorial time, or more like Kung Fu time. This is Top Hat. Use a topology similar to the RC filter seen in class. So you will use, instead of using 1 resistor and 1 capacitor, you will use 1 resistor and 1 inductor. But the shape of the circuit is the same. And then determine the value of the resistor in that RL filter, where you have 1 coil to use as inductor, and that coil is not an ideal inductor. That coil has an inductance of 40 millihenries and also has an intrinsic resistance of 300 ohms. Good. So you have an unknown resistor and that coil that has resistance. We want to create that low pass filter with a corner frequency of 5 kilohertz. What should be the value of that external resistor, that additional resistor? Spoiler alert, here it comes. That should be a 956.6 ohms resistor. Good. You practice on that. Another one. A passive RC high-pass filter has a 20 microfarad capacitor. What should be the value of the resistor to have an approximate cutoff frequency of 3 kilohertz? Please observe that the cutoff frequency is given in hertz, not in radians per second, so take the 2 pi factor into consideration. The answer is 2.65 ohms. Let's review some definitions we made in our class on resonance. Quality factor. For a bandpass filter, we defined the cutoff frequencies omega h and omega l as the frequencies at which the attenuation goes up by 3 decibels. Those are called the half-power frequencies. They define the center frequencies right in the middle of those two half-power frequencies on a logarithmic scale. We found in class that center frequency is computed as the geometric mean of omega low and omega high. That way, square root of omega low multiplied by omega high. The bandwidth is simply the difference between the two half-power frequencies, and the quality factor was defined this way. Just a formula. Good. That was refreshing that lecture on resonance. Here is a tutorial time. Your exercise. Top hat homework. You're given that circuit. That circuit is a bandpass filter. What is the center frequency? What is the bandwidth, and what is the quality factor of that one? That is for you to work at home. I'll give you the answers in a moment. Ready for that? Spoiler alert. So here they are. The answers are: center frequency 1 radians per second. Bandwidth 2.236 radians per second. The quality factor is 0.4472. Good. Remember those results because we will use the circuit again later on in this course. Maybe not in this video, but in the last video of the series. Retake. Remember those answers because we will use this circuit again in the last part of the course, in the last video of this series. And that is all, my students. Thank you very much for watching this second part of the trio of videos dedicated to filters in this Elect 202 course. I hope to see you again in our next video. Good night.